Hey, my name is Reservoir, and I am heading the Neuro and Biomorphic Engineering Lab at the Open University of Israel. This project was led by Avi Hazan, a postgraduate student in computer science in the lab. Reservoir computing is often used to learn dynamical systems. It was shown particularly efficient for fast learning of chaotic and spatiotemporal varied dynamics. Reservoir computing is traditionally implemented using recurrent neural networks, where a pool of recurrently connected neurons is introduced with an input layer and further connected to a weighted output layer. In previous work, we proposed the neuromorphic analog design of a spiky neuron we termed OZ. OZ is a neural engineering framework-inspired neuron, and it can explicitly be defined to feature a programmable response dynamic. Later, we extended OZ to support long-term depotentiation and depression via an analog design of an STDP, spike timing-dependent plasticity synapse. We also previously demonstrated OZ-based real-time learning in high dimensions using an analog implementation of the prescribed error sensitivity learning rule, or PES. In this work, we integrate these analog designs along with a pool of recurrently connected OZ spiking neurons, a reservoir, to demonstrate a neuromorphic analog design of reservoir computing. Our design is a deep and layered circuitry comprising an input layer in which each of 4 inputs is introduced to 4 OZ neurons, an STDP layer in which 8 groups of 8 STDP synapses were connected to the first layer's OZ neurons. A reservoir comprising OZ neurons which are recurrently connected to themselves and to their neighboring neurons, a learning layer comprising PES learning cores which are randomly connected to the reservoir, and finally, an error feedback layer providing an error signal for preceding learning cores. The output of layer 5 is the network's output.
Our circuit design comprised of 3 main modules: OZ spiky neuron, STDP synapse, and PES learning circuit. The analog design of the OZ spiky neuron comprises a voltage-to-current transformation circuitry and a voltage amplifier spike generation circuit. OZ produces a spike train in accordance with its tuning curve or defying rate input current dependency. To support long-term potentiation and depression, we designed an analog implementation of STDP synapse. The synapse is introduced with 2 spike sources, the pre- and the post-OZ neurons. The synapse implements a memory with a decaying factor. To implement learning in a real time, we designed an analog circuitry, realizing the PES learning rule. The weight is implemented as a transistor capacitor memory cell and is continuously modeled using a recurrently connected summing amplifier. The error block can be turned on and off, allowing switching between training and inference working modes. We evaluated a small-scale design of our system with a classification task of the iris flower dataset. Each OZ neuron is characterized by a tuning curve which specifies the neuron response dynamic. First, we tested a 16 neurons reservoir system with 3 different input tuning modalities. We chosen to use a learning rate of 0.002, shown later to be efficient learning hyperparameter. These tuning curves represent different modalities, often used to efficiently span a representation space neuromorphically. Results show that the chosen tuning curve dramatically affect the system performance. We carried on with measuring the performance of the 16 neurons reservoir system with various learning rate and reservoir size. Our results demonstrate that while an 8 neuron reservoir underperformed the higher 16 neurons reservoir, classification performance remained roughly the same when the reservoir size is further increased to 24 neurons, suggesting a sweet point for given task complexity. To conclude, we extended the potential of neuromorphic analog implementation for online learning to rely on the dynamical states of the neurons in a reservoir for providing offline training and online inference.
We would like to thank our funders and partners, and we are looking forward to seeing you all in the conference.